Hi, my name is Ryan Thompson, and I'll be going over merge sort. As stated here, the key to merge sort is merging two sorted arrays into one, such that you have two lists. The resulting list is the combination of the two in this specific order. This is a non-trivial condition of that each array already be sorted. So if you were to look at this and your criteria is ascending order, you would say that this is monotonically increasing. Each array adheres to this principle. And this is the basis for what allows us to do this efficient indexing between the two. So when you're giving two arrays, you are to already assume that these are sorted arrays. Now, since they're each sorted, induction would tell you that the first element is the minimum element of that array. So these are already adhering to the first principle. So we can start at element 1 of each of these and evaluate them accordingly. So again, for the first element, it's evaluating the minimum of y versus the minimum of x. And the minimum of y, which is in position 1, is the smaller of the two values. So we'll put the placeholder in the second element of y and keep the placeholder for x in the same position. We'll continue to evaluate each position in this manner until we've gone through each element of x and each element of y for a total of 8 times. So n is a combination of the number of elements of x and the number of elements of y. So this evaluation criteria is gone through 8 times. Whatever the conditions may be, the number of lines that it's taken the user to write this will only be amplified as n grows. Now, there will always be overhead when initializing the indexing. So for x and j equal 1 for y, that overhead will always be there, but those are constant terms. And in analysis of worst case scenario, ignored. This next part is in addition to the merge and sort. What if you were given an array of size n, in this case 9, and you had no information if this was a sorted or unsorted array. All you know is that you have an array of size n and that you need to sort this in ascending order as dictated by the user. So the first approach that happens is to divide this basic array that you're presented with. And once this array is divided as close to the midpoint as you can, then it will continue to subdivide and subdivide and subdivide until each subdivision only has one element remaining in it. This approach is very clean for powers of 2 because you'll be able to work down to the last element. The last leaf level, the last node level, will always have 1 or n number of elements. But in this case, because 9 is not a power of 2, it'll continue to divide down until one of your node levels only has 2 elements in there, or 2 arrays in there, each with 1 element. Now the divide method, whatever that overhead time may be, times. We'll see that again. So it's called the first time, second time, then the third time, fourth, fifth, sixth, seventh, and finally an 8th time. So that divide time, when you're looking at the total run time for this, needs to be accounted for as well. And now that you've divided all the way down to the lowest level where each array only has 1 element, point where you need to merge the 2 elements together. Now, being only 1 element, they're sorted, and the induction would hold for this. And the maintenance is just once you've gone through each element of the two arrays, and it will terminate once you've reached the end of both of them. So once you've evaluated n number of times, in this case 2, because one element plus one element will give us 2, you're done with this evaluation and you can move back up to the next node. So this is the correct position, or this is the correct position, because 0, it takes the first criteria, or first position. The next position is taken by 4. Now this evaluation method will be evaluated all throughout, so these empty placeholders will be filled in the correct fashion. So grouping, and the next grouping will be aggregated up, and so on. So in the next, we'll see 0, 4 grouped with 86, digital subgrouping. Once these are evaluated against each other, you'll say this is array 1, this is array 2, and it will go through each of the elements. So for any one of these, you could take the number in element or array 1, the number in element 2, and that's how many times you're going to have to loop through total positions to determine if they're in the correct order. You'll see that this is done each time, so it's done for a total of n times. So once you're past that initial level, and that initial level, because it's 9, each of the looping is done n times. So each of this is done 9 times because every single element is evaluated in the merge sort example. To know each position is accurate. So you're always, from every node from this level all the way up, will be done n times. So once you've taken this mid-level, this mid-subarray, and aggregated it back up to 2 arrays, this is a very similar looking to our initial example, and this is y. So this does not matter, again, that this is element 4 number of elements, and this is 5 number of elements. The aggregation or total number is still 9, and it will be evaluated 9 times again, sorted total level. And what you didn't see here is the same approach as done earlier. You know that you have 2 arrays that are sorted. You need an ascending order. Both of those hold that monotonically increasing principle. First minimum of the first array versus the minimum of the second array. 0 wins. You move this down 1, evaluate the new minimum of that array. So you're always evaluating the new minimums, and you know this to be true because these are sorted arrays. Again, here is our final product. These are some notes on the merge sort about memory storage and other requirements that may affect runtime. So if you are memory constrained, insertion sort may be the better method versus merge sort, which will require larger memory storage, so more of a maybe hardware limitation. Because the merge sort analysis is faster, or creates a empty array of the same size of your original array, you get a definite speed increase, but again, it's at the necessity of having the hardware that can handle this. So when you have the power 2, this is a very clean formula, because for every level you go down, the nodes increase. So it's 2 raised to the k number of divisions. And this starts to really demonstrate the power of the merge sort, because you're not having to index on such a smaller scale like the insertion sort. You're able to quickly evaluate big chunks of the array. So the basic approach, again, in a merge sort, is to take an array of initial size, constantly subdivide the array, which will give you a constant uh, runtime requirement that's evaluated the number of nodes that you end up going down. The book says that this is log base 2 times n plus 1, and that will give you the number of times that you're going to have to divide. So if you know that divide has a given time, you'll multiply by that calculation, and that will give you a constant to add to your total runtime. But as we've seen when evaluating worst case scenarios, constants and really look for terms that affect n. So n log n or n squared, things that are the main drivers, not the kind of trivial noise. So once you've divided down as far as you can go, where all the remaining nodes only have one element in there, now you actually call the merge part of this, which will go element and element of each array. So array 1 and array 2, evaluate them against each other because they're known to be sorted, and apply them up to the next node. This is an empty placeholder. These would move into the correct positions. These are at their current places, and then they will be moved into the empty storage and evaluated accordingly. And again, for every node except for that bottom node in this case, because it's an odd number, it's always evaluated n times. So that's a straightforward calculation on runtime from here adding on up. And once this method is, the same method is done for every subarray until you get back, you can see the true power of this method. Thank you.